Okay, hi everybody. Good afternoon. Thanks for coming to the session. This is my first experience with CppCon. It's a great pleasure to be here. Yeah, the automotive industry is undergoing a lot of change currently. You may have seen that or read about this in the press. And this will continue for the years to come, of course. And we will look at a very tiny fraction of this change today. And this is what affects us as programmers. And this is how C++ is used, and is changing the way C++ is used in the industry. And the big factor with this change is adaptive Autosar. So I'll explain a bit what adaptive Autosar is, and then we'll go into and have a look at the coding guidelines that were created within Autosar. Now, this is a car, seen through the eyes of my daughter and through her drawing pencils. And this is what most people in the world probably think of a car. It's got wheels, it's got body, windows, a light in the front, exhaust fumes in the back. That's all you need. Some people know, few people maybe, but still many people know that if you go inside and sit at the driver's seat, and you have dashboard instruments, you may have a meter system, you may have a map display, navigation. So there is some computing going on, there's software, but even fewer people understand that really if you look under the hoods into the car, there's a lot of computing going on. There are these many little control units which control the airbag or control the climate, the brakes, and so on. And this is the realm of Autosar. Autosar is a specification for the basic software in these control units. It's like a platform. And a characteristic thing of these control units is they're small, relatively small. They're often single purpose. They are configured at compile time. You set it up all at compile time. For example, there's never any dynamic memory allocation. You all set up then at compile time, and then it runs. And it's all written in C. So the classic Autosar specification is all in C. Now, where there's a standard, there's an organization behind it, and that's the Autosar Consortium. And this consists of more than 200 partners from all over the industry. Of course, major car manufacturers, hardware suppliers, a lot of software companies, semiconductors, and so on. And I have to mention this once. I work for this green logo in the middle, EB, Electrobit. This is a software supplier, and among many other things, we have we deliver an implementation of the Autosar stack and the tooling for that. Now, what you've seen in the previous picture is not what we need in future cars or in some of the cars which are already on the road today. Such cars have a need for central, high-performing computing clusters, one or many of them. And these computing clusters, of course, they interact with all the other stuff in the car, with a lot of sensors, they interact with the cloud, and they enable us to implement things just as automatic driving. And there's also such functionality as update over the air. So it's a highly dynamic system, totally different than the classic Autosar stuff, and that's what the new specification adaptive Autosar targets. And this is, of course, something which is much more complex than the classic scenario, and therefore the specification requires you to program in C++. Now, there's more on that on this website. You can find more about Autosar and the roadmap and the specifications. So why do we use C++? Well, in fact, we use C++14. So the adaptive Autosar specification mentions C++14 as the language of choice. I think I don't have to explain really why we use C++ over C. That's pretty clear due to the enhanced complexity of these systems. But why do we use C++14? A few years ago, if you had come along with C++14 in the automotive industry, people would have asked, why don't we use C++03? You have, in the automotive industry, you have a lot of long-living code bases, typically, because you have long product cycles, and you have to maintain software over a long time. So you have a lot of existing code there, and you have a lot of competence. But for new things, just like adaptive Autosar, it's clear that we choose more state-of-the-art. And actually, there are also a lot of standards which drive the software development within automotive. For example, safety standards, and they all require you to use state-of-the-art technology and tools. And also, we have to attract developers, which is an important factor. And of course, we can. It's clear that C++14 provides much better alternatives than C++03 for many of the things. So, which has always been a problem in C++03 is unwanted implicit conversions. You can avoid them by just using auto or uniform initialization, or the explicit keyword on conversion operators. You have for-range loop, which you can safely iterate over a container without worrying about running out of range. You can create type-safe function with variable number of arguments, and so on. And of course, we do have to handle concurrency. And of course, everybody knows that the support for concurrency in C++14 is not very large, but at least there is something in there, as opposed to 03, there's nothing in there. So I'm going to show you a little bit what our APIs look like. There is In adaptive Autosar, there's one API, it's called ARA-COM. That's the communication API. So that enables you to communicate with a remote service. Behind that, there's a huge system of specification and code generation out of that. But what it results in code that for the perspective of an application developer, you have this kind of interface. Remote service, and you call a function, and this function is executed in a different process or on a different machine, or maybe even in the backend on the cloud. And what it returns is a future. Now how you get a result, you can just call future get. This of course blocks. If you have a very simple application, then you can afford this. Maybe you have nothing else to do in the current set, then it's okay. But most likely you will need something like this, where you specify a continuation, so a function which gets executed exactly when the result becomes available, and until then you can do other stuff in the thread. That's a common pattern. Little less known, but also possible, is that you have an application which does the scheduling on its own. So you have a loop, and you just ask the future, is the result available? And you get it, or it's not, then you do something else. You grab a task from a queue, and then you go on. And the nice thing is that with one interface, like above, we can support all these models. Unfortunately, only the first one is supported in C++14, and all the others are not even supported in 17. So in adaptive Autosar, we roll our own feature. Unfortunately, but we just do it. So why don't we use 17? 17 certainly provides a lot of interesting features, but it's for the automotive industry, it's just too new at this point of time. There are compilers, that's not the problem, but static analysis tools are not ready. The teaching is not ready. And sometimes you need special compilers. You need compilers which are validated to conform to some safety standards. And such compilers are hard to find and expensive, and they're even hard to find for 11 or 14. So 17 is right now out of question, but we hope that we keep up, of course. So, guidelines. Why do we need guidelines, or specifically guidelines in Autosar? Why did Autosar create them? Why don't we just take them from other sources? And how do we do it? Then I will go into just a bit into some of the topics which are typically controversial within the embedded or automotive industry. See how I handle them. Okay. So, why do we need guidelines? Just start an experiment. Start a software project without them. And the first people who ask you, where are the guidelines, are the developers. They want to know, often they only want to know, do I have to write camel case or Pascal case or snake case? Sometimes they have other questions. And next thing is project managers will ask for it. Quality engineers will ask for it. And you have, again, processes and safety standards, whatever you have to adhere to. So they usually require you to have guidelines and to check them with an automatic tool and so on. But it's not a sufficient reason to just do it because you have to. This is an old quote from Autosar. C makes it easy to shoot yourself in the foot. C++ makes it harder, but when you do, it blows your whole leg up. That's often quoted, and that's also in the preamble of existing guidelines. I was wondering what he would say today. I'm sure maybe something like this. C++ makes it even harder to shoot yourself in the foot, but still you can blow your whole leg off. So you need something to guide. I'm still not satisfied with these quotes because they kind of convey the message implicitly that C programmer gets away more easily than C++ programmers. I'm not sure, so I would ask C programmer, where are you? Maybe he's blown off completely. I don't know. Okay, so we need guidelines. So where do we look? We are in a specific industry, automotive, and we have to maybe adhere to some functional safety requirements. So let's look at the industry, what's there. So one famous, also often quoted guideline is the Joint Strike Fighter Air Vehicle C+ coding standard. That's from 2005, and that's famous because one of the authors was Autosar. This is of course from an area where there are many restrictions, even tighter than in the automotive industry. But it's from 2005. It doesn't address C++14. Then MISRA. MISRA is the Motor Industry Software Reliability Association. They have created guidelines for C, and they have also created guidelines for C++ in 2008. And that's, if you do C++ in the automotive industry, then you come across these guidelines. Tools support them. Customers require them. They're everywhere. But, of course, it's not C++14. So it covers maybe safety, critical systems, but it's not 14. So let's look at more recent work. There are high integrity C++ coding standards. I've seen them used in the automotive industry as well. It's pretty good work, focusing on C+11. But it's not quite what we need in detail. There are the CERT coding standard, which is up to date. It's very good work. Focuses on security. And of course, the CppCon guidelines. So none of this to say that any of this is bad, but it's just maybe not sufficient, or maybe have a different focus. At least what you have to do is you have to review all of these and see if they fit to the industry at hand. And that's what Autosar has been doing and is still doing. So Autosar invested in doing this research and setting up guidelines because there was nothing there. I will cover this data, how we see this in the long run. Also, it's not actually an organization whose main focus is to maintain such guidelines, but we do it right now just to give it a start. So our approach was to go through the MISRA guidelines, because they are the quasi-standard in the industry, go through them and then check if they make sense still for modern C++, delete rules or add rules for new features. As that was the start, and then we went through all the other guidelines that I mentioned and checked if we can take over rules from them or have to modify stuff. And the great thing is that the document we've created creates huge tables of traceability to all the other guidelines. So this makes it easier for tool developers or tool configurators to actually map the Autosar rules to existing rules. And there is a version published, from March this year. There was the first release of Adaptive Autosar, and the guidelines also came along with that. And you can download this under this website. It's available publicly. So at this point, this is my reminder. I have to give some credits. There's a group within the Autosar consortium which works on these guidelines. I'm in this group, but I'm by far not the person who does the majority of this work. So there are a lot of other people and companies who contribute, and I'm just supposed to present this as the Autosar work, but in fact there are a lot of other people behind which deserve the credits. So let's look at some of the rules. Single return. Single return is a rule which you can find in a lot of the existing older standards, in the MISRA standard, even in the JSF standard guideline, I should say. It's not standard. For example, MISRA says a function shall have a single point of exit at the end of the function. Now, this is a problem. Because why is this a problem? It just doesn't work. In C++, by default, unless we know explicitly otherwise, we have multiple exits, we have exceptions. So MISRA has a workaround for this, so they have an exception to the rule, which covers exceptions, and this is called throw an exception that is not called within the function is not considered a point of exit. I don't know if that helps. It probably helps MISRA to work around this effect, but really doesn't help much. And then we did a little bit of research, what actually reason why this rule is in there. And the reason is that it's in many of the safety standards. And if you look in the safety standards, it says something like it's highly recommended to have single exit. But it doesn't give a rationale. That's a bit of a sorry situation. So that's basically the reason why MISRA keeps the rule in, but we decided to do otherwise. We dropped this rule. And well, we have to prepare for some maybe reviews or audits and have to give reasons for this, of course. And here are some reasons. Why can we afford to drop this? This is C++ code. Very simple, but very common. So we instantiate a vector, local variable that allocates memory, of course. We call a function that may throw an exception. Is this a problem? No, it's not, because When an exception is called, the destructor for vector will be called, and this will deallocate the memory. If we just simply go out of scope, and the function will also deallocate the memory. So this is for experienced programs, it's a trivial pattern, and it's as old as the language itself. It's called use resource acquisition. Resource acquisition is initialization. Just have to use it, and you never have any problem with resources. By the way, there's a generic resource wrapper that you may want to have a look at. Just link down there. So the mantra of use C++ trainer is usually use RAI. You can turn this argument around. Since you use RAI, you don't have to worry about multiple exits. But you can see where this rule comes from. It comes from C, of course, where you don't have this function. There's another reason. Code which has a single return often looks like this. So you have this, what's called the arrowhead anti-pattern. The code looks like an arrowhead, and the interesting part is somewhere in tip there. And sometimes you have bits repeated then on the way out. It's much simpler just to write it like this. And the second reason is code which has a single return or forces you to have a single return needs to introduce a temporary variable. And what's the problem here? Well, there is no problem here right now, but there could be a problem if we extend the code or modify it. We could forget to maybe we add another branch here, so we may access result without having initialized it. So potentially we have a problem here, which is bad enough, and this is called, with a fancy name, it's called a data flow anomaly, a UR anomaly. So you could access a variable which is undefined, and you reference it. So you fix it. Assign some value, but then you have the problem in a different place. Then you have in the first branch you assign a value and you never use the previous value, so you have to find it and unuse it. That's the DU anomaly. Or you define the same value it already has, so it's a double define. So all three of these are not wanted. And actually, if you look at the MISRA guidelines, they already require you to avoid these anomalies, and Autosar guidelines require you to avoid them as well, but Autosar can achieve it. Okay, exceptions. Another topic which is traditionally very controversial in the embedded industry. Dates back to old times when compilers generated large code or generated performance overhead. These times are long gone, but sort of the prejudice still sticks sometimes. What does MISRA say? MISRA C++ say about it? I say it could have advantages, could be a clear means of handling error conditions, but it's sort of, piece of code that's difficult to understand. It's basically saying, well, we don't know how it works either. They don't give any further guidance on how to use them correctly. Core guidelines say essentially there are a lot of language facilities and especially library facilities which just make use of it, of exceptions. So you cannot typically avoid having to deal with exceptions. Maybe in some restricted, very tiny subset, very special problems, you can, but in general, you cannot avoid it. So what we say is we don't force anybody to use exceptions in their own code, but you should be prepared to deal with exceptions that are thrown by other code. But if you use them, then you have to follow some rules, and like roughly 40 rules in the guidelines to handle exceptions correctly. And one of the major rules is don't use them for control flow. And another thing is, which is sort of a characteristic of the systems we're dealing with, we have this last-ditch catch-all thing. So in the main function and in every thread main function, we catch all exceptions. The reason for that is if you don't do it, then standard terminate will be called, which leads to exit of the program, which may or may not unwind the stack completely, which may or may not, typically won't, call the destructors of static objects. We want to make sure that this is a program always exits sanely. So every resources are deallocated. So even in a very fatal, unexpected error exception that you don't handle somewhere else, which creeps up to the main function, we guarantee a safe exit. Which is important because often the scenario is then that maybe your program shuts down, but it may be restarted by some other monitoring process, and it's important that you really start from scratch with all the resources deleted. Typical concerns that people have about exceptions: it sort of introduces or may introduce a hidden control flow. You have an additional exit point from functions. What can you say about the state of a program when an exception is thrown, and so on? Important points are also runtime performance. What can you say about worst case execution time? The hidden control flow we cover by this rule. We say a function shall not exit with an exception if it's able to complete its task. So that's another way of saying don't use it for control flow. So this example, there's a function which computes a CRC from a message, and it computes the result, it completes its task, so it should not throw an exception. Instead, it just should return a value. Which doesn't mean that this function should never throw an exception, but just when it completes a task, it should not throw an exception. It could still throw an exception. It actually does throw an exception. You see stat. Yeah, when a message is empty, the @0 will throw an exception, which is perfectly in line with this rule, because the function cannot then complete its task. Obviously, having a non-empty message is a precondition, and this is violated here. So some are worried about additional exit points. We have covered this before. We are not worried about multiple exit points because we can handle them by using RI. that's the usual rule. You have to ensure that the program state is correct. So you have to provide basic guarantee always, or the strong guarantee if you can, and the no-throw guarantee. Write the no-except keyword, and so on. What about runtime performance? Now that depends, of course, highly on the compiler you use. If you use GCC or Clang, then you have a zero-cost exception handling implementation. That means you don't have, as long as the exception is not thrown, you don't have a runtime cost. So depends on what you use, but these, especially GCC, is heavily used in automotive as well. Worst case execution time, that's a difficult topic. So what happens when an exception is thrown? Can you make a statement about at least the worst case the program executes? You probably want to ensure that even if you exit the program via the main function and via this last-ditch catch thing, that this will execute in a deterministic time. So, and that's somewhat difficult to say it. You have to measure it, of course. You have to analyze the behavior of your runtime system, or you have to go ask a compiler vendor to provide this guarantee for you. You may find that actually maybe the exception handling or throwing exception involves a memory allocation, and you may find that this is not usually the factor which causes a lot of runtime normally, but it could cause an undeterministic behavior. So you may change the memory allocation strategy. So all kinds of things you can do. The guidelines would say you have to sort of analyze this and make a statement about this. Okay, this brings us to next topic, dynamic memory. This is also often sometimes controversially discussed, especially for people which come from the really hard embedded world where everything is static and pre-allocated. So, but you need dynamic memory. So often you have data, you know the size only at runtime, or you have data which is dependent from object lifetimes, especially when you share data between different threads. The promised future pattern requires you to share data on the heap. You want to employ something like type erasure. That typically requires dynamic memory stat function. It has, of course, small object optimization, but in general, it requires dynamic memory allocation. You use library features, some language features like exceptions. You throw an exception that typically causes a memory allocation. Containers from the standard library. Of course, you can customize them by writing allocators. Stat function you cannot customize because that customization is deprecated. It's deprecated in C+17, but effectively this means it's already deprecated now. We cannot use this. So you can say like the same thing that we say about exceptions. Few programs can manage to avoid dynamic memory allocation, unless you have very specific problems. Typical issues: memory leaks, memory fragmentation, non-deterministic execution time, running out of memory. Memory leaks we handle easily with using write. Consequently, we forbid, and that's a rule in the guideline, actually, there should be no delete, and new and delete explicitly should always go via the standard containers or the smart pointers. Memory fragmentation, that depends less on the language, but on your system, on your operating system, or on, if you write allocators on your own, of course you have to ensure that they don't fragment memory. But there are techniques available for that. That's the thing that is probably specific for the automotive industry, that you want to guarantee also here a worst case execution time. And this is not always easy if you use the standard operating system OS, malloc and free, or new delete. So you typically want to override this, or maybe you get away with just using custom allocators for your containers. And out of memory, well, you have to look at your system. You have to, typically you can specify a maximum memory. You do that implicitly already when you design hardware. You can do it for the software as well. So the typical thing is you use pre-allocated memory and allocate from there. Okay, how are we doing for time? Oh, that's good. We have some. So I didn't cover many C++14 features, so let's look a bit at how we handle these new features. Lambdas, that's not a new rule. You can find this in the Scott Myers books, or also we always want to explicitly capture stuff, not use the implicit capture, because it's easier to control than what you actually capture and modify. A simple rule, we always write the empty parameter list, even if that is not strictly required by language. We don't nest the lambdas, because if you allow people to do that, well, it leads to bad code. I've seen it. Auto is another topic which is, there's a lot of prejudice or anxiety among people, especially when they come from C. What Auto does, it's not as scary actually. We allow it. Well, the rule is we allow it. Oh no, the rule is it's actually not. It's forbidden except in several cases. That's the way it's written. This maybe reflects the sort of skepticism which is around in the industry about Auto. You could also have written it like use Auto to avoid application, or use Auto to avoid implicit conversions that you don't want. The result is the same. So we allow Auto when you want to capture the value which is returned from a function, like in this first example, vector size. We allow Auto when you want to initialize a primitive type. Well, you don't have an any other chance with the lambda, of course. Otherwise, other variables like an integer, we always initialize without auto. There's another reason here, because we want users to not use int, but always to specify the size. So use the standard integer types, int32 underscore t, for example. And if you would write auto I equals 42, you would end up with int, and that's usually not desired. And we also require the curly braces. So there's some other cases where you actually can't do without auto. The parameters for generic lambdas or return type deduction. Is there also stuff we forbid? There was a lot of stuff that we actually allow, or in contrast to all the guidelines, it looks like we're very liberal, but there's also a lot of stuff we forbid. So we forbid atomics and threads and all these primitives from application code. We just have them in special library code, of course, but we want to get away with them in typical high-level code. These rules are not ready yet, but this is the way they will go. We forbid explicitly delete. I've already mentioned that. Most of the casts, because they usually indicate bad design, dynamic casts also introduce some indeterminate, or could introduce undeterministic timing behavior. WCHAR and score T, that's platform defined, and a lot of the legacy C style variadic arguments, standard IO, something like that's the stuff we don't allow. Okay, so I was talking about change in the beginning, and this is a major change, because adaptive Autosar is like the first major scale specification which brings modern C++ to the automotive world. There has been a lot of C++ already in other domains outside of Autosar. There have been, of course, also projects running C++11 or 14, but this is a large-scale thing. So expect that in the future there will be more C++ and more modern C++ in your car. There will hopefully be more talks about modern C++ by people from the automotive industry. There are guidelines, which are the first ones which comprehensively handles C++ in combination with automotive-specific requirements. The guidelines are still work in progress, they're incomplete and everything, but it's a start. So how will it go on with the guidelines? We'll continue analyzing the existing rules from other standards, complete the traceability tables. That work, I think we will complete until next upcoming release. There's one coming up in autumn. We will work on rules for standard library usage, which probably won't make it into the release. I've already mentioned some rules on multi-threading, on atomics, and threads that are work in progress currently. A big thing is tool support. We won't be doing that. That's not Autosar's intention, but we are in contact with tool providers so that the Autosar rules can be supported by tools. And eventually, and this is the important thing, eventually we want to hand these rules over to some other organization, which is more capable and more suited to maintain such rules in the long run. Unfortunately, I cannot tell you right now which organization this will be. Maybe this will be a profile in the CppCon core guidelines. I don't know. There are discussions going on around this, but I have no information really which I can present right now. Not even the timing. There is a release of Autosar, adaptive Autosar, coming up this fall. It says 10/17. That will be October. Don't hold me for the date. This will include more APIs and more enhanced reference implementation for the APIs, and also will include an updated version of the guidelines. Okay, thank you. Are there any questions?
Adaptive Autosar standards, is there intent to work with the new generation of self-driving cars, or is it mostly focusing on the complexity of the control systems that are already in vehicles?
The question was if there's intent of the adaptive Autosar standards to work together with the self-driving cars. So the technology for self-driving cars is not something which will be developed within Autosar. It will be developed probably by companies which are also in the Autosar consortium, but it's not part of the Autosar specification. But the Autosar specification provides a platform. It's an enabling technology. So on top of that, you could run an application which enables self-driving. And there is work, or has just started work in the consortium to cover parallel computing. There will be some API for that, but their details are not fleshed out at the moment.
The reason people usually prefer to use plain C format programming is that sometimes they say the closing brace is just a closing brace.
Sorry, what? I didn't get the last part.
Closing brace is just a closing brace. So basically, you don't have some hidden behavior like structures firing out, going out of scope, stuff like this.
Right.
In your presentation, the stuff I see is all good programming practice, basically, but doesn't answer the question of how this code would live in hard real-time environment, which cars are. So basically, on 600,000 RPM, a usual engine does like 50 Hz firing events, which is like a medium graphics engine, but it needs to do it with full redundancy and fast and listened by FTTs is crucial in some applications. So basically, how does this spec enforce hard real-time constraints, or does it even attempt to target this area?
just in a way, but it's also up to you, as if your task is to write an application which has hard real-time requirements, then you would use maybe the subset of C++ which enables you to do exactly this. And
So problem is that what applications does it target? Is it engine control units directly controlling the engine, or is it some high-level stuff like power systems?
It's more the high-level stuff. The classic world with the smaller control units and with the hard real-time requirement, that will still remain. So we will have both worlds for a while. The SAE?
Society of Automotive Engineers, the kind of theological society that you were considering handing off Autosar to.
I would have to look this up if they're in the consortium, or maybe there have been talks already with them, which I don't know if it's possible.
One last question.
Yeah.
Is Tesla involved?
No, not to my knowledge. So, thank you very much again. Goodbye.